Hello all, thank you for joining me. And today I'll be presenting on some research I did this past summer under the mentorship of Dr. Mary Alberg on the UD anti-quark asymmetry in the proton sea. So just starting out with a brief introduction to the proton. We understand pretty well from deep inelastic scattering and D'Orléans experiments that the proton is composed of three valence quarks, an up and up and a down, in addition to quark anti-quark pairs, which we call the quark C, the proton Z. And finally, there are also gluons, which hold it all together. So with this in mind, we first began by constructing a statistical model of a proton using a method developed by Zhang et al. So we consider these three reactions here. We have a gluon radiating a gluon. We have a gluon decaying into a quark-anti-quark pair, and then also a quark emitting a gluon. And then we consider all the different possible states of the proton. So for example, down here, we consider the up-up-down state, and we compare that with the up-up-down gluon state. And to go from the first to the second, there are three different possible reactions. All three of them are each of the quarks just radiating a gluon. Similarly, if we're to go in the reverse, we would have the gluon and any one of these quarks recombining to form just a quark. So we are three in one direction, three ways to go in the other direction, so both states are equally likely. If we now consider this up-up-down gluon and up-up-down with two gluons, again, we have each of these quarks radiating a gluon. That gives us three possibilities. We also have a gluon radiating a gluon, which gives us a fourth one. And if we were to return, we have this lower reaction, a quark and a gluon combining to form a quark, and that can happen 6 times since we have 3 quarks and 2 gluons, and then we also have the gluon recombination. So that means that our first state is 7/4 times as likely as the second state. And we then generalize this to all states involving 20 particles, and that we included then U bar pairs and D bar pairs, and we generalized this for all 20 or fewer particle states. And this was a good start. However, this model was fairly crude. So my advisor, Dr. Mary Alberg, and one of her colleagues, Miller, had developed a different model called the Meson cloud model. And here we represent the proton as an epoxy expansion of meson baryon pairs. So we have a proton is some bare proton in addition to a bunch of meson baryon pairs into which the proton fluctuates. For example, a neutron and a pi plus, or a proton and a pi naught, or we even looked at delta particles, so a delta naught and a pi plus. And in our final representation of the proton for this project, we used Alberg and Miller's chiral light front perturbation theory and some of their experimental data to reconstruct the meson baryon pairs. However, we did not have a bare proton. So that's where we're going to take our statistical model and input it into our bare proton. However, before we do that, our statistical model was a model for the full proton and not the bare proton. So we want to make sure that we input our statistical model. We're not counting meson baryon pairs in our statistical model, which are also in the bare, which are also counted here. So we have to subtract out the meson baryon pairs. So if we consider, for example, the up-up-down D bar state from a statistical model, we can view that as, for example, a neutron and a pi plus, and this would be one of our meson baryon pairs. However, we could also group it as a DUU and a D bar, which would give us our valence quarks in the C, which would be part of our bare proton. So we went through our statistical proton and subtracted out all the meson baryon pairs, leaving us with just the bare proton terms. Once we had our bare proton, we then used a program called Rambo to perform Monte Carlo analysis and generate a momentum distribution. And then once we had our momentum distribution, we evolved that up to 54 GeV squared to compare with experimental data, since the scale that we were working at was far too low to be comparable to any experiments out there. Then we inputted it into the Meson cloud model, and previously, my advisor had also done the same technique with a bare proton developed by Zurich. And here in green, we show our model, In green, we show Stirrick's model. In black, we show ours. In blue are the data points collected by E866. So you can see for the D bar minus U bar distribution, we're both relatively good, and that's fairly standard. At this point, most theoretical models model the D bar minus U bar fairly well. However, for the ratio, you can see that initially we fit it fairly well. However, we become off much later on. And this is most likely because our bare proton tends to dominate out here. And we found this was mostly because our bare proton was much stronger at large X than the rest of the Meson baryon pairs. We believe this is due to not evolving it enough, since evolving it shifts the distribution to lower X. And when we did our evolution, we believe our initial energy was around 0.03 GeV squared. However, the DGLAP equations we used for evolution are only valid at around 2 GeV and higher. So we just started evolving them from 2. However, there's a large difference between the 0.03 and the 2, which we assumed were roughly equal for all intents and purposes now. So we believe that our beta would be much better fit if we were able to perform this evolution at much lower energies. If you have any questions, please feel free to reach out, and thank you for listening.